So this is a classic mechanics problem that you may or may not have come across before. And it's always one that I try and tell people that if you can solve this problem, you are going to do pretty well in any mechanics exam that you're going to come across, and you have a pretty genuine understanding of the concepts that underlay things. And the thing that makes this problem difficult, challenging, scary for students is the lack of information that you're given. So let me lay it out for you. The problem is you've got a child sitting on top of an igloo. So the igloo is frictionless, there's no friction, and the child just starts to move, let's say. So the child just starts to slide on the igloo. And the question we're asking is, okay, so let's imagine we'll draw a straight line here. The question I'm going to ask is, there's a particular point where, if you can imagine sliding down, the child is going to come away from the igloo. So they're not going to, stay stuck to it all the way to the ground. They're going to slide down it, and eventually they're going to come unstuck from it, if you like. So the question is, at what angle, theta, which I've marked in there, does this happen? And you might ask, is that it? Is that all the information you're going to give me? Do I not need the height of the igloo? Do I not need the mass of the child and all that stuff? And the answer is no, you don't. And that's what throws a lot of people. When you solve a lot of mechanics and kinematics problems, you can get good at them, you can get smart at them, you can say, right, I've been given this information, and that kind of leads me to believe that I need the following to get through the problem, and so on and so on. Here, there isn't a single number you're given. You're just given a scenario and asked to solve it, and it's a bit of an intimidating problem. And as well as, that aspect of not giving away too much information, it also, when we see the solution now in a few minutes, you'll see that it takes into account kinematics, it takes into account circular motion, it takes into account your trigonometry, and it takes into account kinetic and potential energy. So, as I said before, if you understand this question even, and if you can solve it on your own, all the better. But if you can understand this one, you're doing pretty well. So it turns out that the key to solving it is to start with energy. So we know, we've looked at, say, dropping free fall motion. Sorry, couldn't come to me. We've looked at free fall motion, and we said at the beginning of free fall motion, before we drop something, say, out of a window, all the energy is potential, and the object has zero kinetic energy. Then just as the object hits the ground, it's got all kinetic energy and zero potential energy. So we've got something similar here. So we've got a situation where the child is sliding down the igloo, and it starts off with zero kinetic energy, and all of its energy is potential by virtue of the height on the igloo. So, and we know from the law of conservation of energy, but because there's no friction on this igloo, the total energy of the child is going to be the same at any point on it. So we can write down KE1, so this is going to be our kinetic energy, plus U1, which is our potential energy, is going to be equal to KE2, which is our kinetic energy at any other point, plus U2. So this is just point 1 and point 2 are, point 1 is going to be the top where the child is sitting here, and point 2 is any other point on the igloo. So this relationship holds all the way. So let's think about what those values are at point 1 first of all. So we've said that the kinetic energy is 0. So that's going to give us 0 here, plus what's the potential energy of the child here. So what's, in terms of the igloo, so I'm not sure if I stated already, the igloo is semicircular, as I've drawn it there. So that turns out to be a pretty key point of the problem. So, how do we work out the potential energy? Well, let's say the radius of our circle here is r, then the child is going to be at a height r above the ground here. So their potential energy is going to be given by m, their mass, times g, the acceleration due to gravity, times r, which is the radius of the circle. Now, at any other point on the circle, what is their energy going to be? So their kinetic energy at any point then is going to be a half mv squared, as we know well. How are we going to work out their potential energy? Well, if we look at our angle theta here, let's draw a straight line across here. So what we can see is that as that angle theta increases or decreases, the height above the ground that the child is going to be equal to r cosine theta. So the length of this segment that I'm drawn in black here is going to be r cosine theta. So as the angle theta increases, our r cosine theta here is going to decrease. So the potential energy at any point now is going to be equal to mg times r cosine theta. R cosine theta. So let's write that in. So this is going to apply to any point, depending on what the angle is at that point. So now we've set up our energies, and we've got some unknowns here. So we don't know the radius of the circle, so we can't, plug that in. We don't know the mass of the child. So I'm after telling you at the start of this problem that we don't have the mass, we don't have the height, we don't have any of that stuff. But now I'm after delivering an equation based on the energy, the balance of energies, and it looks like we need both of those things, and it looks like we need V to be able to solve it. Sorry, I should have put a plus in here rather than an equals. So how do we solve it? Well, there's another way we can look at the problem, is that it's a circular motion problem. So we can write that in here. So there's, the child is going to be moving while the child is stuck to the igloo. That's in this part here, which I'm drawn in black. The child is moving in circular motion. So we're going to have circular motion, which means that we're going to have a centripetal force. So let's see if we can do something with the balance of forces now, like we did with the balance of energies in the earlier part of the problem. So if we draw a sort of a free body diagram, let's say at this point here. So let's imagine that the child is at some arbitrary point here on our circle. So we'll take it down here. We'll just draw in the circle. We'll draw in the point where the child is. There's going to be a normal force keeping the child on the igloo. So the normal force is the reaction, the familiar reaction force between the child and the igloo. And there's going to be the child's weight acting in the opposite direction. So the child's weight in the opposite direction is going to be equal to mg cosine theta. So if we look at our triangles, we can figure out, or we can sort of make the identity that this length here is going to be equal to mg cosine theta. So mg is acting downwards here. So this is our mg. Theta is going to be in here. So these two are going to be similar triangles. So theta is going to be in here. And this side here is mg cosine theta. And then this side here, which I'm drawing badly here, is mg sine theta in our right angle triangle. So the balance of forces then, the centripetal force, so that's going to be sigma, the total centripetal force is going to be equal to, we're going to have mg cosine theta acting sort of downwards in the radial direction, if you like, so towards the center of the circle, minus the normal force Fn acting outwards radially. So those two forces are going to be balanced, and the net force then is going to be the net centripetal force, which is mv squared over r. So this is our balance of forces in the radial direction due to that circular motion. So what is that going to tell us? Well, we need to evaluate what we're looking for at this point. So we have our balance of energies, we have our balance of forces. So when does the child come unstuck from the igloo, if you like? Is there anything in the notation that we've written down so far that tells us when the child will leave the igloo? Well, we said that it's the normal force that's keeping the child in motion, in circular motion. So if you can imagine, once that normal force goes to zero, that's the point where the child becomes unstuck. So if we look here at our circular, or at our igloo in the top diagram, if you can imagine, once this normal force goes to zero, now the child's motion is going to look like the black arrow that I've drawn in here. So once the normal force goes to zero, circular motion stops and the child becomes unstuck. So we can say then that contact with the igloo, contact is lost once n goes to zero. Let's see, when n goes to zero. So that's the point that we're looking for. Sorry, let me go back here and change my notation. Where am I? Oh, gosh, I'm making a mess of it. So contact is lost when Fn, sorry, I just fixed my notation, goes to zero. So let's look up above and try and work out that equation. So we know that Fn has gone to zero, F subscript n has gone to zero. So we're looking for the point where mg cosine theta minus zero, so minus Fn is now minus zero, so we can leave that out, is equal to mv squared over r. So this is the angle. So if we solve for theta here now, that's going to give us the angle that we need, and that's going to give us the angle that the child leaves the igloo at. The problem again is that we don't have the information that we need to solve for to solve for theta. So we don't have the mass. That doesn't matter because these two masses cancel out. We don't know the velocity, and we don't know the radius of the circle. Sorry, I'll just put in a capital R there. I just made a mistake with my notation. All we can glean then from this analysis of the circular motion is that v squared is equal to g times r cosine theta. G times r cosine theta. But what we can do now is take this piece of information. So let's put a box around it. So we can take this piece of information that v squared is equal to g times r cosine theta and bring it back to our energy analysis that we did above. Plug it in, and what we'll find is that lots and lots of things are going to cancel out when we do that. So we now have this expression for v squared in terms of things that we already have in our energy analysis, and it's all going to work out nicely. So let me sort of do that for you just to highlight it. So now, if we go back to our energy equation here, so let's just put a box around this one and say, right, so on the left-hand side, we've got 0 plus mgr. So 0 plus mgr is going to be equal to half mv squared plus mg times r cosine theta. So that's just rewriting what we had above in this first boxed equation. So what does that look like now when we make that substitution for v squared that we got from our circular motion analysis? So on the left hand side we've got mgr equals a half m, but now v squared we've shown to be equal to g times r cosine theta. So now we've got a half m times g times r times cosine theta plus mg r cosine theta as we had earlier on. So what we've done with this step, so going from here to here, we've gotten rid of v squared out of our equation. And now you can see that there are lots and lots of similar terms across this equation now that we can get rid of. And when we do our cancellations, what we're left with on both sides is 1 is equal to 3 over 2 cosine theta. So in that one magic step, we've gotten rid of the need to know the mass, we've gotten rid of the need to know the radius of the circle. So all of that stuff cancels out, and we're left with 1 equals 3 over 2 times cosine theta. And what that tells us then is that theta is equal to the inverse cosine of 2 over 3, and that's equal to 48 degrees. So that's the answer that we come out with, is 48 degrees. So as you can probably guess, that is it's a really tough problem. I mean, if you're stuck in an exam trying to solve that one, good luck to you. It's not going to be that easy. You know, you could sort of spend an hour just trying to work out how to go about it, never mind the steps that you need to get it to work, realizing that you need to use circular motion and solve for v and substitute in. So it is a really tricky problem. And as I said, even if you can, work through the solution and understand all the steps involved in the solution, that alone, is going to tell you that you've got a good understanding of what's going on in Newtonian mechanics. And then if you wanted to build on that yourself, you could introduce some friction. So you could say, right, the coefficient of static friction or of kinetic friction of the ice in the igloo is, say, 0.1, and try and rework the problem and see what the angle is then. So that would, that might be something you could go off and do now after this, watching this video, try and figure out how to include friction in this problem. But it's definitely a good one to get your head around.